Hi and welcome to leg stretching, and while we're doing the leg stretching I'm going to read a bit about the ventral nerve cord, and participating in the exercises is at your own risk. So let's start with the first exercise. We're bringing one leg in front with the heel to the ground, and we're putting the toes towards us, and we're stretching this way, this leg, and now every couple of times we are contracting the quads, and we are still stretching for a few seconds. And then we're releasing the quads again, but we are still stretching. So the ventral nerve cord. Different types of animals exist. So there are different types of animals, and we're contracting again the quads and stretching. There are animals who have no spine. So there are animals who don't have a spine. And release the contraction, but keep the stretch. The spine is composed out of a bunch of vertebrae stacked on top of each other. And we're contracting again. So the spine has lots of vertebrae stacked on top of each other. They are called vertebras. And we release again. Animals who do not have a spine have logically no vertebrae which would compose the spine. And we're contracting again. Animals who do not have a spine and therefore no vertebrae are so-called invertebrate animals. And we're releasing the contraction again, but keeping the stretch. So animals who don't have a spine have no vertebrae which would be stacked on top of each other in the spine. So they are invertebrate animals. Invertebrate, they don't have vertebrates. And we're contracting over last time. And animals, for example, which are invertebrate animals are ants, crabs, butterflies, and bees. And we're releasing contraction, and we're switching and taking the other leg in front. And we are stretching and contracting the quads. The central nervous system regulates many different body functions, coordinates body movements, processes what the senses feel, and we're releasing the contraction again, but keeping the stretch. The central nervous system is mainly in the brain and spine. So the central nervous system is in retina also, but it's in the brain and in the spine. And it controls coordination, it coordinates body movements, it controls different body functions, and processes also what the senses all feel. And we're releasing the contraction again, but keeping the stretch. The central nervous system is mainly in the brain and in the spine. And we're contracting again. Inside the spine there is the spinal cord, which is a more precise place where the central nervous system is in the spine of vertebrates. So vertebrates have a spine with vertebras, and inside we're releasing the contraction. Inside of the spine with the vertebras there's the spinal cord. And this spinal cord is part together with the brain and the retina. But this spinal cord is the central nervous system. There's the central nervous system. And we're contracting again for last time. Now, invertebrate animals don't have a spine with a spinal cord, but they have a ventral nerve cord, which does the equivalent job as the spinal cord. And we're releasing the contraction again, and now the next exercise. Now the leg onto the side, the toes are pointing in the same direction as we are doing with our main part of the body. And now we are bringing the leg in, so we are pressing the back leg into the ground. No pain anyway here. So if there's any pain, you have to stretch when you're doing too much. And so we're pressing that leg into the ground and a bit to us into that direction. Vertebrates have a spine with a spinal cord, and invertebrates, bees and ants, don't have a spine with a spinal cord, with a central nervous system inside of a spinal cord, but they have, and we're releasing the stretch a bit, but invertebrates have a ventral nerve cord. Vertebrates have a spine with vertebrates and a spinal cord with a central nervous system regulating the body function and movements. Invertebrates do not have a spine with vertebrae, they don't have a spinal cord inside of the spine, but a ventral nerve cord doing the same work of regulating the body functions and movements. And we are driving the leg again into the floor. Vertebrates have a central nervous system in the spinal cord. Invertebrates have a central nervous system in the ventral nerve cord. So, vertebrates, like humans, spinal cord, and invertebrates, butterflies, ventral nerve cord. And we're releasing the stretch again, and we're switching to the other side. Again, leg on the side, and the toes are pointing forward, and we're driving the leg into the ground. And a bit more. Some extracts from the article neurotransmitter identity is acquired in a lineage-restricted manner in the Drosophila CNS. by Halukla Hui-Min Jin, Xi Long, Robert H. Singer, Tsu-Min Lee, James W. Truman, and we're releasing the stretch a bit. Under the section abstract is written: the vast majority of the adult fly ventral nerve cord is composed of 34 hemiplegias, which are clusters of linearly related neurons. And we're stretching again, driving the leg into the floor. Neurons in these hemiplegias use one of the three fast-acting neurotransmitters, acetylcholine, GABA, or glutamate for communication. And we're releasing the stretch again, and we're doing the next exercise. Now the legs on the side, the torso pointing again to the outside. We're flexing the foot, and we're turning the leg up and back down again. And we are more or less keeping with the main part of the torso into the front direction. We generated a comprehensive neurotransmitter usage map for the entire ventral nerve cord. We did not find any cases of neurons using more than one neurotransmitter, but found that the acetylcholine-specific gene CHAT is transcribed in many glutamatergic and GABAergic neurons, but these transcripts typically do not leave the nucleus and are not translated. And I'm switching and doing the same on the other side, and we're going to read that one sentence again. And turning out and in again. We did not find any case of neurons using more than one neurotransmitter, but found that the acetylcholine-specific gene CHAT is transcribed in many glutamatergic and GABAergic neurons, but these transcripts typically do not leave the nucleus and are not translated. Importantly, our work uncovered a simple rule. All neurons within a hemiplegia use the same neurotransmitter. Thus, neurotransmitter identity is acquired at the stem cell level. Our detailed transmitter usage lineage identity map will be a great resource for studying the developmental basis of behavior and deciphering how neuronal circuits function to regulate behavior. And so now, the next exercise, we're going into the 1990 position. So this leg has 90 degrees and that leg has 90 degrees. We're pointing with our hands to our knee, which is behind us. And now we're going forward to the forward leg. And then is written under summary of this article: this study examines the fundamental question of how neural progenitive cells and the lineages that these give rise to relate to the specification of neurotransmitters. The authors investigate this question in the Drosophila adult ventral nervous system, focused on the fast-acting small molecule transmitters, ACH, GABA, and glutamate. To this end, the authors used sophisticated genetics, previously developed by the authors and their collaborators, to visualize each post-embryonic neuroblast hemilineage and turn by assaying for the expression of these three fast-acting neurotransmitters, assayed by detection of GABA, CHAT, and V-glut using antibodies and in situ hybridization of genetic reporters for GAD1, CHAT, and V-glut expression. And now on the other side. Again with the legs 90-90. And the hands go to the leg which is behind. And we're leaning forward. Here the authors have undertaken to describe the neurotransmitter and T identity of each of those post-embryonic lineages. They find a simple rule governs this choice. All neurons born from a single hemilineage share the same NT identity. They demonstrate this through high-quality in situs to detect glutamateric, GABA ergic, and cholinergic identities and show that NTs are first clustered and second mutually exclusive in the Drosophila VNC. Based on the clustering, they propose a possible hemilineage-based mechanism underlying NT identity. Based on the mutual exclusivity, they propose that lineages must make only one type of NT neurons. And we're changing again into the 90-90 position, and now we're going forward and just stretching. I want to read that sentence again. They demonstrate this through high-quality in situs to detect glutameric, GABAergic, and cholinergic identities and show that NTs are first clustered and second, mutually exclusive in the Drosophila VNC. Based on the clustering, we propose a possible hemilineage-based mechanism underlying NT identity. Based on the mutual exclusivity, they propose that lineages must make only one type of NT neurons. I read that sentence again. Based on the clustering, they propose a possible hemilineage-based mechanism underlying NT identity. Based on the mutual exclusivity, they propose that lineages must make only one type of NT neurons. And if you like to, you can go now into the pigeon pose. Do this only if you can do it without to injure yourself, and if you know already how the pigeon pose works, because it looks for everyone differently. We go on to demonstrate this by relying on old and new NB-specific tools, combined with antibody labeling for NTs. They also do the converse, use old and new NT-specific GLs, Lexas, split lines to assign NT identity and identify lineages using molecular markers, cell body position, and axon tracts. Importantly, they often use multiple approaches, reagents to demonstrate NT identity and demonstrate the exclusivity of NT identity for each NB hemilineage. Finally, in the process, Lacey et al. Have once again generated excellent reagents and body of reference, both of which will be invaluable for the community. The study is exceptionally well done and beautifully presented. This is an outstanding description deserving of publication in eLife. And now we are switching to the other leg. And under Essential Reviews is written our again 1990, and we're gonna go forward. Essential revisions. Our concerns are largely to do with text and ease of digesting this wealth of information. And I'm going to read again that section abstract. The vast majority of the adult fly ventral nerve cord is composed of 34 hemilineages, which are clusters of linearly related neurons. Neurons in these hemilineages use one of the three fast-acting neurotransmitters, acetylcholine, GABA, or glutamate, for communication. And if you like to, and you know how to do the pigeon pose without to injure yourself, you can do now the pigeon pose. We generated a comprehensive neurotransmitter usage map for the entire ventral nerve cord. We did not find any case of neurons using more than one neurotransmitter. The sentence again. We generated a comprehensive neurotransmitter usage map for the entire ventral nerve cord. We did not find any case of neurons using more than one neurotransmitter, but found that the acetylcholine-specific gene CHBT is transcribed in many glutamateric and GABAergic neurons, but these transcripts typically do not leave the nucleus and are not translated. Importantly, our work uncovered a simple rule. All neurons within a hemilineage use the same neurotransmitter. Thus, neurotransmitter identity is acquired at the stem cell level. Our detailed transmitter usage lineage identity map will be a great resource for studying the developmental basis of behavior and deciphering how neural circuits function to regulate behavior. And we are done stretching. And we're now sitting in butterfly stretch. So just with the grounds of the toes together. And we're trying to be straight with the back and leaning a bit forward. So that sentence again. Importantly, our work uncovered a simple rule. All neurons within a hemilineage use the same neurotransmitter. Thus, neurotransmitter identity is acquired at the stem cell level. Our detailed transmitter usage lineage identity map will be a great resource for studying the developmental basis of behavior and deciphering how neural circuits function to regulate behavior. So, there are different types of animals. There are animals who have no spine. The spine is composed out of a bunch of vertebras stacked on top of each other. Animals who do not have a spine have logically no vertebras, which would compose the spine. Animals who do not have a spine and therefore no vertebras are so-called invertebrate animals. Animals without a spine and which are therefore invertebrate animals are, for example, ants, crabs, butterflies, bees. The central nervous system regulates many different body functions. The central nervous system is mainly in the brain and in the spine. Inside the spine there's the spinal cord and there's the central nervous system is the center of the brain. And so vertebras have a central nervous system in the spinal cord and invertebrates have a central nervous system in the ventral cord. of course also brain. I thank you very much and have a next time.